Yes.
Fantastic. It's my pleasure to announce the talk of Kathrin Bringmann. She will do modular completion for us. Please take it away, Kathrin.
Thank you very much. And please feel free to interrupt. So I am not going to speak the whole time anyway, because I'm much too fast when giving BIME talks. So really ask if there are any questions. Now it doesn't want to move anymore. Now it is moving. So I want to say a little bit about modular forms and Jacobi forms first. But I'm assuming people know what modular forms are. I'm just going to give the basic examples I need. Then I will speak about harmonic mass forms, even though we've already seen them during this conference. I also require non-holomorphic Jacobi forms. Then I want to speak about false theta functions, and sometimes they're multiplied with modular objects. Those are mixed false theta functions. And then I want to finish with speaking about some functions considered by NORB and how to complete them. So everyone knows modular forms, and just to set notations, the examples I need are the modular theta function, just summing over the squares. There's a modular form of weight 1/2 for gamma 04. And one nice feature is that you can use it to count representation numbers. Namely, I'm using always vectors in bold notation. So if I count the number of representations of n1 squared plus n2 squared plus n3 squared equal to n, then those are the coefficients of theta cubed. And one nice thing about this is that there's a formula relating those numbers to the so-called Hurwitz class numbers. This is due to Gauss. And the Hurwitz class numbers count SL to Z equivalence classes of binary integral quadratic forms that have discriminant n, and they have a certain weighting. But then one might wonder, if one goes back to the identity, on the one side, one has clearly a modular object, a modular form of weight 3/2. Why is this right-hand side modular? And we'll see that in a minute. Another class of functions I need, and those later relates to my functions of NORB, are related to binary quadratic forms. So I let Q sub D for a positive non-square discriminant be those integral binary quadratic forms that have discriminant D. And I can sum over all of those. And this is a function that's been studied, for example, by Dorn-Zaki, and it's related to the Doll-Nakanuma lift. And it turns out that this function is a modular form. It's a cusp form. And if kappa is 1, then you need to do the Hackett trick to also show it's a modular object. My third example is related to so-called partitions. Partitions are non-increasing sequences that sum to a given number n. And I let P of n denote the number of partitions of n. So for example, the partitions of 4 can take 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, or all ones. And if you count those options, then we have that P of 4 is equal to 5. So now one nice thing about the partitions is that if you put them in a generating function, you have this nice infinite product expansion, which is due to Euler. And this is a really pretty analytical object, which in turn can give a lot of information about those coefficients P of n. And in terms of modular object, this is basically one of the eta functions. So the partition generating function basically has weight minus 1/2. So now what does modularity mean in this case? I can write it down for the generators of SL to Z. And under translation and inversion, the function is mapped back to itself up to this simple multiplier. The one nice thing about the partition function is that it satisfies simple congruences. Those were found by Ramanujan, and say that P of 5n plus 4 is divisible by 5, P of 7n plus 5 is divisible by 7, and P of 11n plus 6 is divisible by 11. And Ken Ono showed then that there are infinitely many congruents. And he used highly sophisticated methods like Serre's theory of half-integrated modular forms and Galois theory to show that you have infinitely many of those. And you can give nice explicit examples, can write down many of those congruences. However, the ones found by Ramanujan are the simplest ones. Now, in order to explain those congruences, Dyson introduced the so-called rank of a partition. So the rank of a partition is the largest part of a partition minus number of parts of the partition. And just to state an example, I'm listing here the ranks of all partitions of 4. So I already gave you an example, the partitions of 4. Here they are. Here I'm listing the largest part. And here the number of parts, and they're all the ranks. And if you look what these ranks are, mod 5, then you see that each congruence class is hit exactly once. So that gives you an explanation of the partition congruence in this one specific example. And we're going to show that this always holds. So in particular, if you go back to the congruences, we can use the rank to explain this partition congruence. And the same is true mod 7. So then what about generating functions? Now we have two things that are actually moving. We're looking at partitions of n, and a rank is given. So we have a 2-variable generating function. And Atkin and Swin and Dyer showed that this has this nice generating function. So it's a Q-hypergeometric series, but it can also be written in terms of this lattice sum. And this lattice sum representation is important for modularity later on. And one particular example, you can, for example, use the second representation and plug in zeta equals 1. Then this factor basically goes away, but the n equals 0 term gives you a pole, so that cancels, so you get the partition generating function. And if you plug it into this representation, you actually get the Q-hypergeometric series representation for the partition function. Now, I already mentioned that Dyson's rank explains those first two congruences. In order to also explain the final one, the mod 11 one, Dyson postulated the existence of another statistic, which he called the crank, and which should explain all congruences. So the crank is defined as follows. The crank of a partition is the largest part of the partition if O of lambda is 0. So if O of lambda counts the number of ones in the partition, and it's mu of lambda minus O of lambda if O of lambda is bigger than 0, and mu of lambda is the number of parts that are bigger than O of lambda. So if we look at the cranks of the partitions of 4, I list it again here. List the largest parts. I list O of lambda, mu of lambda, and here the crank. And if you again look what happens mod 5, you see again every residue class is hit exactly once. And the same is true mod 7 and mod 11. So again, let's look at the generating function. I let mn be the number of partitions of n with crank m. And due to Andrews and Garvin, we have this following generating function. Now it can be written as this nice infinite product, which immediately gives you modularity properties. And again, you can write it as a similar looking function as the rank generating function. And again, the partition generating function is the first case. And using this modularity, Karl Marburg was able to show that there are infinitely many congruences for the crank, which then decompose the partition congruences. One thing we'll also briefly need later are so-called quasi-modular forms. They occur as pieces of so-called almost holomorphic modular forms, which behave like modular forms, but are polynomials in one of the imaginary part of my variable, and the coefficients are holomorphic. And if you take then the constant term, you get a quasi-modular forms. So you can view these almost holomorphic modular forms as completions of quasi-modular forms. The most famous example is the Eisenstein-Sears E2. That's a quasi-modular form, and you add this simple polynomial in the imaginary part to obtain E2 hat, sometimes it's called E2 star, which transforms of weight 2. And also derivatives of modular forms are quasi-modular forms. And they're also related to Jacobi forms. We'll do that next. So Jacobi forms, I briefly mentioned, since maybe not everyone has seen them, are functions now of two variables. The first one should actually be an H, not a C. And we have now a modular transformation. The second one should be an H, sorry. And we now have a modular transformation law and an elliptic transformation law. And also notice if you plug Z equals 0, this transforms like a modular object. And then again, as for modular forms, we want some growth condition. So an example, similar to the theta function before, is the Jacobi theta function. So this is basically like the theta function before, but we have this extra piece, linear piece with my z variable. And this is a Jacobi form of weight 1/2 and index 1/2. Already mentioned, if I plug in z equals 0, I get a modular form. And I can also differentiate with respect to my Jacobi variable and then set z equals 0. And I get, again, a modular form, but the weight goes up. And you see that immediately if you look at the transformation law. If you differentiate this factor doesn't contribute if I then in the next step set z equals 0. So I just have to differentiate this function and this function on the left. And if you look at Taylor coefficients, so take higher derivatives of Jacobi forms, then you obtain quasi-modular forms. And you also immediately see that when just writing down the transformation law and differentiating it. And one example related to what we had before, if you remember the crank generating function, this infinite product, this is basically up to powers of q and powers of e to the 2 pi z, eta squared over the Jacobi theta function. So it's a meromorphic Jacobi form. And poles come from roots of the Jacobi theta function. Now we're interested in moments of those. So those come about when you differentiate the crank generating function with respect to your Jacobi variable. And one can show, because this is a Jacobi form, that one has quasi-modular properties. So let me next move to bit more complicated objects. We've already seen it during this conference, so-called harmonic mass forms. And we're again looking at functions on the upper half plane, but now instead of being holomorphic like modular forms or meromorphic, they're just real analytic, and they're annihilated by the weight k hyperbolic Laplace operator, which I just recall here. And again, we want growth conditions. And one nice thing about harmonic mass forms is that split in a holomorphic part, which looks like a modular form, the Q series, and a non-holomorphic part, which has an expansion in incomplete gamma functions. And often the holomorphic part is also referred to as a mock modular form. And the non-holomorphic part has another representation as this integral, this non-holomorphic integral. And in the integrand, you have a modular form, a classical modular form, which has dual weight to what you're starting to. So it's weight 2 minus k if the starting function has weight k. And you can recover this function in the integral by basically differentiating with respect to tau bar and then conjugating again, and then multiplying with some power of the imaginary part. And this operator, the psi operator, which goes back to Brunier and Funke, maps harmonic mass forms to modular forms. So one specific nice object related to these harmonic mass forms are the so-called mock theta functions. Those were introduced by Ramanujan in his last letter to Hardy, and he wrote the following: I am extremely sorry for not writing you a single letter up to now. I recently discovered very interesting functions, which I call mock theta functions. Unlike the false theta functions, they enter into mathematics as beautifully as the theta functions. I'm sending you with this letter some examples. And whenever Ramanujan speaks about theta functions, he just means the normal modular forms. And the false theta function that he also mentions, I'll also show you in a minute, and I'll also explain how they can actually be embedded in a modular framework. So in the spirit of Ramanujan, let me just give you an example of such a mock theta function. So my favorite mock theta function is the mock theta function f of q, given as this q hypergeometric series. And I just denote for the following the coefficients of this mock theta function by alpha of q. And note that alpha of q, one can show, counts the number of partitions with even rank minus those with odd rank. And it's also easy to see, if you remember the hypergeometric series of the rank generating function, that if you plug in as root of unity just -1, you get f of q. And Sander Sveges in his PhD thesis then famously showed that this mock theta function is a mock modular form. So he found an explicit piece you can add. You can write it as an expansion in incomplete gamma, as I've shown you before, or as an integral to obtain a harmonic mass form. And then jointly with Ken Ono, I considered the general rank generating function, and we showed that for any root of unity, you get a mock modular form. And you can actually do this more general. You can also take a root of unity and multiply by a power of q, and then up to some q power in front, you again get a mock modular form. This has many applications, including partition congruences, asymptotics, and identities. So now let's return to the class numbers. Let's look at the class number generating function. I asked before, how is this related to modular objects if I take certain linear combination? I restrict to the residue classes that give you theta cubed. And it is actually a famous result, which goes back to mainly Zaki, but also Hirzebruch and Zaki, that you can complete this Hurwitz class number generating function by adding this integral involving the theta function. And the function in the integral, one also calls the shadow of the Hurwitz class number generating function. And that then also explains this identity. If you restrict to the residue classes, you can show that the corresponding linear combinations are modular, and then you have an identity between modular forms, and then you just use finite dimensionality of the space. And can also generalize this. So we have now seen that if I apply this Xi operator, I get a modular form. You can also go up in level and just demand that applying Xi reduces one depth, and those are then the higher depths mock modular forms. So having, let's say, depth 3, I apply Xi, then I have a depth 2 object. So now let's look at non-holomorphic Jacobi forms. And I was mainly interested in those because of things coming from ranks. It turns out that the rank generating function isn't quite a usual Jacobi form, but some non-holomorphic Jacobi object. And I was interested because I wanted to study moments of those, again, as for the crank. And remember that for the crank, those were quasi-modular forms. So the question arose, like, what is true for the rank? And I found the following completions. So I define my rank moment functions, again, having like a holomorphic and a non-holomorphic part, now a bit more complicated. So the holomorphic part involves my moments and some power of the eigenstantiers E2. And the non-holomorphic part involves, like, the main piece is this function S, which looks like a theta function, some non-holomorphic object. So it's like a theta function, but it has an extra term being the error function. So this V should actually be a tau 2. And then I showed that this object actually transforms modular. So this is just some multiplier of weight 2L minus 1/2. And there's also some really nice relation. If you apply an operator, namely if you apply the mass lowering operator, then we get this really simple function. So basically eta and some power of E2 hat. So now what is actually the key? So the key is that we're interested in certain functions which transform like Jacobi forms, and can show that this rank generating function, the completion of that does that. And then the idea is to Taylor expand in my holomorphic variable and look what the behavior of the remaining part is. And then one can take linear combination of those objects. One plugs in z bar equals 0 and takes appropriate linear combinations. And this is actually a finite sum because you don't have very high order poles. And then this object, this appropriate linear combination has the right modular transformation behavior. And I was able to use this to then prove modularity of my completions. And then one can also directly just compute the action of the operators. So now let me come to false theta functions. I already mentioned them in the quote of Ramanujan. False theta functions are like theta functions, but they have wrong sign factors.
I'm very sorry to interrupt you, but will there has there already been leaking of some modular forms to the lower half plane, or is it happening to be?
No, I haven't mentioned that, but yes, you're right. There is a definite leaking from mock objects to false theta functions.
Okay, fantastic. Will you talk about it?
I will not talk about that, no. Because I'm mainly interested in one object at a time and how to complete those objects. So unfortunately, the completions, you don't really see that leaking. So basically, what you can do is you can write the false theta function as an integral and then go up to the other half plane to see the mock completion piece, but you don't see the holomorphic parts. It's not like holomorphic part goes to holomorphic part. And in this talk, I'm mainly interested in like starting with the holomorphic object, how can you complete it?
Okay, thank you so much.
Yeah. So here I'm giving an example of a false theta function. So this goes back to Rogers. And so one property about these false theta functions is that they are so-called quantum modular forms. So following Don Zage, these quantum modular forms live on a subset of the rationals, and they have some kind of modular behavior here, in the sense that the difference, so this would be 0 if it would be a modular object, that is just nice. And this should just include many examples. And that's why it's kind of formulated very vaguely. And this is my quantum set. And an example of such a form are the false theta functions. Particularly nice such false theta function is the so-called strange function, Kontsevich. So I'm defining this false theta function, which is basically an Eichler integral of the eta function, just the Legendre symbol. And there's a strange identity saying that this object is equal to this series. And it's equal in quotes because as a Q series, the right-hand side doesn't make sense, but you can evaluate it at roots of unity. And taking it as radial limit, it makes a lot of sense, meaning then you have a convergent series here. It's finite, it's terminating. And that is then equaling to the limit of this series here. And the example that I'm particularly interested in comes from so-called unimodal sequences. So those are sequences that go up to one peak and then go down again. And those should add up to some given number n. Those are called unimodal sequences, or sometimes in the literature, they're also called stacks. And I let u of n be the number of unimodal sequences of size n. And again, let's look at the generating function. And this time, I have a modular prefactor, and I have this extra piece, which isn't quite a modular object. It's also called partial theta function because it's only summing over half of a lattice. And then I can define my false theta function, which just goes over full lattice, but then has a sign factor here. And using this, I can write my unimodal rank generating function as this false theta divided by eta power and this extra modular piece. Now, one can use the work of before, like work of Zage, to know that this function has actually modular properties on the rationals. It's a quantum modular form. But then we're wondering what happens on the upper half plane. And can actually complete this function to an object which transforms modular the following way. So basically, we turn the sign into an error function. And then notice that this original false theta function is a limiting case of this completed function. And I was able to show jointly with Caner Nazaroglu that this function transforms like a modular form. And one key application was that we're actually able to get asymptotics for unimodal sequences. So those were first studied by Oleg and Wright, and they showed the asymptotic main term, which actually looks a lot like the behavior of the partition function. And we were then able to write down an exact formula for unimodal sequences, looks as follows. So the first piece looks exactly as an exact formula coming from a modular form. But then we have extra terms, which now involve integrals of Bessel functions. And this looks pretty terrifying, but it's however not so bad because you can approximate these integrals really well, do saddle point approximation, and then write down as many terms in the asymptotic expansion as you want. So it's actually a really good approximating formula. And the idea is just to use the circle method and modular completions. So another place where these false theta functions come about is in vertex algebras. So the class of function I was studying with Andrew Milas are those objects. So we're looking at certain false theta functions given as follows. So again, a sign factor. You're now restricting certain congruence classes, and we're dividing by either. And then, so these are our objects. And then we can write down the asymptotic behavior. I guess like this is mentioning a little bit this leaking that you're saying, because so here I'm seeing that I'm having a companion, and this is basically what this leaking is about. I'm finding another piece which has the same asymptotic behavior, and this is my companion. So this is the object that is on the upper half plane, the other half plane, and this you could actually write also as an integral. There you see that it leaks the other half plane.
Oh, okay, thanks. May I just make a tiny little comment why I was talking about the leaking of this function, and why I was particularly asking this question, because in this talk when I was mentioning that we will find some generalized Eisenstein series, the condition on the vanishing of the coefficient looked like some very weird Ramanujan type sum that looked like a shifted Ramanujan type sum on the divisor function. And when we were trying to evaluate the sum with like elementary method, it was looking like the sum should be at least very formally be equal to the Fourier coefficients of some modular form are summed together with its component, and when we take a square of it, once again that was like super formal and a very non-rigorous, and then there were no functional equations of that.
Excuse me, I'm not sure whether this is stuff for final discussion later.
I'm very sorry, and that's what the reason was. I was like asking about the leakage and the functional equation, maybe.
Okay, thanks. So as I mentioned, you can also write these as integrals, and you have in the integrand you have certain modular objects. So these are modular forms of weight 3/2. And then actually jointly with Chanair, I could use our theorem before the modularity to write down how these false objects behave. Namely, there's some mark false behavior. So you can look vector evaluate. So this difference is equal to some nice function, and we're able to explicitly write down what this is. And that gives you, this is just some multiplier. This gives you the quantum modularity of these objects. It recovers it, it gives like a more systematic proof. And then I want to finish with some functions of knob. So he was studying some kind of quadratic form type Poincare series, like I showed you in the beginning. But he looked what happens if you formally integrate those and got certain log terms. And that raised the question, what about modularity properties? So they're not quite behaving modular, but is there like any way to put them into modular framework? So he wrote down the transformation of those. So instead of mapping to 0, which they would under inversion if they would be modular, one gets these extra pieces. So can one somehow repair that? And to do that, I need some more functions. So there's a function that's introduced by Parson, and she studied similar quadratic form series, but with the restriction that A is positive. And we also need certain geodesics. These are given here. So my quadratic form is always ABC. And these are these geodesics counted, taking all points in the upper half plane where this Q sub tau is equal to 0. And then I want to take the union of those. And then I need 2 more functions, which I require for my completion. So again, everything is written in terms of quadratic forms, somewhat simple functions. And then I can actually write down my completion. So I have my original function, I add the parson function and these two other objects. And then jointly with my student Andreas Mono, we showed the following. This function transforms modular actually in two variables. The first variable has weight 2k plus 2, and the second variable it has weight 0. And now the main question is like, how does it complete the function? So if you take the limit, my second variable going to minus infinity, then I recover my original function. So very similar to the false theta function, I can get the original function, the transformation of that back from my completion by just taking a limit. And if I take the second variable and I go to infinity, I get 0, so it's some cuspidal condition. And this completion is holomorphic with respect to tau and anti-holomorphic with respect to my second variable w. And if I plug in what would be the most natural thing to actually do, w equals tau bar, then I get 0. So that actually shows that the function has to be more complicated. So you can't just do this very simple plugging in. So what's the idea of proof? So translation invariant is immediate. And modular inversion, you just look at the individual summons. So this first transformation law is already known by Knob. And then we look for all the summons, how they transform. So the second piece gives you some extra terms. The lambda transforms really nicely. And then the key is to just use certain roots for complex logarithms and see how things nicely combine to see that in the end, all the obstructions cancel out and you get a nice modular object. Then this limit behavior, you again look at the individual pieces, use roots of logarithms and show that this first piece is just 0. Then you recover the function that you want. And the third property, so this is that the cuspidal condition. I basically just need to show that I can interchange the limit with the summation. So I need good convergence. Then the fourth property is just direct calculation. And then the final one, let me just go here again, that I plug tau, when I plug tau equals tau, w equals tau bar, it's actually pretty lengthy calculation, complicated roots of log to show that this gives 0. So you have to look carefully at the branch cuts and then see that everything, the whole function actually cancels out and you just get the 0 function. And I've finished much earlier, so thank you for your time.
Yeah, thank you very much, Kathrin. Then we have plenty of time for discussions.
Yeah.
Who would like to start? And then I start by asking, Kathrin, in your work with Terry Gannon and Markus Berg, where you looked at massive deformations of mass forms and modular graph forms, which parts of your talk are most closely related to those?
I wouldn't say, I mean, in some sense, these are kind of somewhat like Eisenstein series, but not really, right? So I wouldn't see it's really related other than that there's also some kind of modular object. But there we were more looking at like functions that lie above those, whereas here I'm more completing objects. So I wouldn't really say it's very closely related.
A question by Sol. Kathrin, you showed us a double generating series for partitions and ranks and one for partitions and cranks. Is there a triple generating series, a series with 3 variables that encodes all 3 of those pieces of data?
So I hear someone saying something really softly, but I can't really.
Kathrin, can you hear him?
Yes, now I hear.
Okay,
great.
So you showed us a double generating series for partitions and ranks.
Yes. And
another for partitions and cranks.
Yes.
Is there a generating series in 3 variables that partitions, ranks, and cranks?
No, I'm again not hearing you.
Okay, we're trying to work on the, sorry, we're getting the tech guy to help us out, I hope. Just a minute, please. Hold on. Okay, can you hear me now?
Very softly, but barely. You sound very, very far away.
Just a minute, please. We're trying something else.
Speak into my computer.
Kathrin,
Yeah, now it's great.
so you showed us a double generating series for partitions and ranks,
Mhm.
and another double generating series
Mhm.
for partitions and cranks.
Mhm.
Is there a triple generating series? That is a series in 3 variables that includes partitions, ranks, and cranks?
No, so there is a series where if you put different parameters, you can recover all of those, but it doesn't have more variables. It's more like you have an extra parameter. Like if I don't know how I move. Let's go to the Lurch type sums. I have to move a little bit. This is actually, I can, this is quicker. So what's known is if you look at this function here, so there is a function which encodes ranks and cranks where this 3 here moves. So if you go to the crank, you have a 1 here. So there's one function which encodes that, but not having like, I mean, in some sense it is a parameter, but it's not like an extra variable where 1 gives the rank and the crank. So I don't think anyone has studied that, but it is like one family which includes both of them. But I don't think anyone studied a function which has more variables. Like if you plug one variable equal to 1, you get the crank, one variable, get the rank. I don't think anyone has studied that. I guess the question is, what would be the hope? So could you get any more information? Because this is really nice because it gives us an analytic object which gives information about the coefficients. So would that give any more information which I can't encode in this one yet?
Okay, thanks a lot for your elaborate answer, Kathrin. Any further questions?
What was the motivation for the knop?
For the?
For the knop to introduce the functions?
I mean, not basically, he looked at all kind of new function. I mean, this basically, it goes back to this first example here that I showed you. So this modular type object that has occurred in a lot of settings. So that occurs in like when looking at lifts, for example, when looking at question of vanishing of L functions. And what Knopp was doing, he was just formally integrating this function. Then he got something which actually was divergent. So he just changed some sign and then asked what object is that? Does it have nice properties? So in some sense, he found it pretty ad hoc, but then wondered, does it maybe give you something? And the answer is yes, it does give you something. But it basically came about by like saying, can I generalize this function which naturally occurs in several settings?
Okay, thank you.
All right, we do have time for more questions, but we already had a couple of
Any
them.
more questions, anybody?
Yeah, if not, then let's thank Kathrin again. So now I'm not sure what the master plan is in case we have extra 20 minutes. Oh yeah, then let's have Manish going on slide sharing mode. Manish, are you around?
Yes, I'm around, yeah. Okay, let's try this. Perfect.
Okay, short break and get together again at past. All right.
Okay.
Hey Manish, we can see your slides.
You can see my slides, okay?
Yep.
Okay, let me just, there's one more thing I need to check.
The fact that it's loud in here has nothing to do with transmission. So we need to check whether he can hear you. You need to check whether he can hear you at all.
Can you see when I write on my slides?
Manish, just to check, can you hear us?
Yeah. Yeah, I can hear you. Can you see when I write on my slides?
Oh, yes, we can
Yeah,
see that.
Yeah, okay, good.
Thank you.
And you can hear me okay?
Oh, yeah, acoustics is fine.
Okay, perfect. I think you also heard my daughter scream there.